Hello and welcome to this lecture on bioeffects and safety of ultrasound. So we know that ultrasound can be used to destroy tissues and other objects, and as I will explain later, those effects are used in medicine, but because we know that it can be used to destroy tissues, we know that they will have an effect on tissues. So any ultrasound could have an effect on tissues. Diagnostic ultrasound to this date has not been shown to be in any way dangerous to a human being. However, the possibility is there. Therefore, we have to be very careful when we use ultrasound, when we use diagnostic ultrasound, and we have to be very much aware that the theoretical possibility is there. So in terms of bioeffects and safety, we distinguish between thermal and non-thermal effects. The non-thermals are mostly the mechanical effects. These will be depicted on your screen when you're doing an ultrasound study. And I'd like to start with the ALARA principle. As I mentioned, ultrasound has not been shown to have any deleterious effect on a human. However, because the possibility is there, we have to keep our scanning as low as reasonably achievable. So that's the ALARA. It stands for as low as reasonably achievable. So shortest amount of time, diagnostic imaging, and bearing in mind that you wouldn't want to keep the ultrasound probe in one place for too long, and you would only use it for diagnostic or educational purposes. The thermal effects can be used for example, catheter ablation, to coagulate tissues, to destroy tissues. So the high frequency focused ultrasound is used for catheter ablation. And going on to standards, originally they described different intensities that they were allowing for different modalities of ultrasound imaging. So there was a different intensity allowed for vascular or cardiac or fetal or eye purposes. However, they simplified this, so now there's only one standard for all imaging, which is 720 milliwatts per centimeter square intensity, and there's a lower one for ophthalmic. So for eyes you need to use less strong ultrasound. And there's this ODS, which is the output display standard. It means that every single ultrasound machine will have to display it on its screen. How much is that TI and MI, the thermal index and the mechanical index? I will get to that in a moment. Usually it's in the corner of the image, and MI is the mechanical index, TI is a thermal index, and you really should pay attention to these numbers while you're scanning and try to use the ultrasound system so that these will not exceed recommendations. So let's continue on with the thermal index. As you see here, thermal index can be thought of as the current acoustic power output over the power required to raise the temperature by 1 degree Celsius. So in broadly speaking, if the TI is 2, then it means that your surrounding tissues will be warmed by about 2 degrees Celsius. It doesn't really mean that, but you can think of it that way. So the higher the number, the more heat will be produced. And as we discussed earlier, this is due to absorption and attenuation, and it is a property of all ultrasound systems. There are 3 different thermal indices that we distinguish between. TIS is meant to be used for soft tissue imaging. TIB is when bone is deep, for example, for fetal imaging, so like the fetal bone, the fetal skull, like deep in the ultrasound field. TIC is when bone is close to the surface. So for example, transcranial Doppler or something similar. Thermal effects will be depending on your output power. So the higher the power, of course, the worse the thermal effects. Transducer frequency, again, we discussed this earlier. The higher the frequency, the more possibility there is for the ultrasound beam to interact with tissues, and that will lead to increased thermal effects. Your focal zone position and your depth of imaging will be important, and mode of operation as well. Very important is your tissue characteristics and blood supply, and that's why they came up with these 3 different thermal indices. They found that there's greatest heating on bone surfaces, and then the heat will be transferred into soft tissues from there. And again, the theoretical possibility exists that you can, with increased temperatures, you can induce necrosis of surrounding tissues and cell death of surrounding tissues. That's why these thermal effects are very important. And if you think about the characteristics of the ultrasound pulse, you see that there are a few different ways of describing that ultrasound pulse, as well as the ultrasound beam, and then how the intensity is looking in terms of spatial arrangement and time arrangement as well. So there's this SPTA concept where they're looking at the spatial peak and the temporal average, and this is what we use, and they describe the highest intensity according to the spatial peak and the temporal average of that ultrasound intensity, and that this relates to thermal effects, and it must be less than 720 milliwatts per centimeter square. So it really, what it means is that it's the highest intensity that's measured at any point on the beam, and then they average it over the pulse repetition period. There are FDA standards, of course, for ultrasound usage, and the maximum allowable increase is 2 degrees Celsius. Most likely the fetal tissue will be more sensitive to thermal effects. However, the maximum 2 degrees Celsius increase should be okay for fetal tissues as well. So for the moment, that applies to fetal tissues as well. Let's move on to the mechanical effects. Mechanical effects are the cavitation and microstreaming. And as you see here as well, that for a more focused and a stronger ultrasound, cavitation effects can be used as the effect itself can be used for lithotripsy. So again, I just wanted to highlight that you can use ultrasound to destroy objects and to destroy tissues. So that's why you have to be very careful with living tissues as well. Cavitation occurs when sound wave interacts with microscopic gas-filled bodies. There's 2 types of this cavitation. There's the stable cavitation, where these little bubbles will grow and then just start to resonate or oscillate. This is thought to be a bit less dangerous. And the other type is the transient or different names. There are different names for this inertial or normal cavitation, where these little bubbles will grow and then violently collapse. Theoretically, both of these can have an effect on surrounding cells and tissues, and both of these can destroy cells, so they can interrupt cell membranes and they can destroy surrounding cells and tissues. The other type of a mechanical effect is microstreaming or radiation force, which is just a transfer of momentum of ultrasound into the tissue or into the medium, and it will cause some displacement. So as you heard from a previous lecture, the basis of ultrasound and sound propagation in tissue is actually this displacement. So it will occur in any tissue at any time. Mechanical effects will depend on the pressure amplitude of your sound wave, so that is related to the loudness of the sound, so the amplitude of your sound wave. Transducer frequency will have an effect as well. As you see here, mechanical effects are related to the peak negative pressure, which is the rarefaction zones, and the transducer frequency. Also, exposure time is very important, so you need to limit the time you spend for scanning. Pulse repetition frequency as well. If there are gas bubbles already present, so for example in lung tissue, the mechanical effects will be more pronounced. And single beam ultrasound modes are worse in this, so M mode and pulsed wave Doppler are worse in this. And I'd like to mention in this lecture ultrasound enhancing agents or ultrasound contrast, and they will need a modification of the mechanical effects of the ultrasound beam. So in a further lecture, I'll be talking about this a bit more, but just be aware that when you're using ultrasound enhancing agents, you really have to think about this mechanical index, and you have to have a low mechanical index mode when you're using these contrast agents. So standards describe the maximum allowable mechanical index, which is 1.9, and it's going to be depicted on your picture. Much less for ophthalmic uses, and the maximum thermal index would be 6, but that's only allowed for about a minute, and this becomes more important in toe imaging, really, where the ultrasound is really very close to the tissue. If you use too much color flow or pulsed wave Doppler, you might get a warning from your system that you need to stop using the color for a while. The mechanical and thermal index is usually depicted on your image, and you really have to pay attention to these numbers. These were my resources, as always, so feel free to look up these papers. They're all very good, and I would recommend reading them. They're all very good in describing these quite difficult concepts. And then the textbooks that I use and some of the images I took from, again, I would recommend you buying them. These are really very good books with very good explanations. So thank you for listening, and I'll see you next time on a future talk.